Right now, while you watch this, China is making a black thread thinner than 1/10 of a human hair that can reach engineering tensile strength above 8 gigapascals and industrial output measured in hundreds of tons a year. That sounds like a lab stunt. It is not. It means the material of the next industrial age may no longer look like a beam, a rail, or a plate. It may look like thread. If this kind of shift is the thing you want to understand before everyone else does, hit subscribe right now. Because this story is about to get much bigger. You see iron every day. Bridges, cars, trains, towers, shipping ports, factory frames. Iron and steel taught you a rule. If something needs to be strong, it needs to be heavy. But that rule is breaking, quietly, and China is pushing the brake faster than people realize. The material is called T1200 carbon fiber. The number matters. In this grading system, a higher number means higher tensile strength, and every jump gets harder to manufacture. Think of it like climbing a staircase, where each next step is twice as steep as the last one. China National Building Material Group says its SYT80 T1200 grade carbon fiber exceeds 8,000 megapascals in engineering tensile strength. State reports also say it has a density about 1/4 that of steel and tensile strength, roughly 10 times higher than ordinary steel. In simple terms, imagine a steel cable turning into fishing line without giving up its job. That is the mental shift. This is not just lighter material. It is a new answer to what strength can look like. Scamp Chemnet, CGTN. And then came the demo that made the story feel real. According to Scamp, state television showed a rope made from 120,000 carbon fiber filaments with a diameter under 2 millimeters when taut, strong enough to tow a coach carrying 54 adults. That image matters more than any chemistry lecture. A bus full of people is something you can picture. A black cord thinner than your charging cable dragging that load changes the room. The number that made engineers go quiet was not only the strength, it was the combination of strength and scale. Because a miraculous sample in a lab is one thing, a repeatable industrial line is another. Most people will never hear this part. Materials revolutions do not fail because science stops working. They fail because factories cannot hold precision hour after hour. Scamp. That is the problem iron never solved. When machines must fly farther, move faster, carry more payload, or waste less energy, every extra kilogram becomes a penalty. In rockets, weight raises launch cost. In drones, it cuts range. In wind turbines, it limits blade length. In pressure vessels, it steals useful capacity. A 2022 review in Composites Part B said carbon fiber can offer about 10 times higher specific strength than aluminum and steel, depending on the fiber used. Specific strength means strength compared with weight. That is the detail that changes everything. A bodybuilder can lift a lot. A marathon runner can move that strength across distance. Industry increasingly rewards the marathon runner. Carbon fiber gives machines that kind of advantage. Science Direct. You can already see the proof in aviation. The same review noted that the Boeing 787 and Airbus A350 use airframes with more than 50% composites by weight. That happened for a reason. Aircraft punish dead weight. A lighter frame means lower fuel burn, better range, or more payload. The analogy is simple. If you had to carry groceries up 10 flights of stairs, you would not choose a cast iron backpack. Aerospace solved that lesson years ago. The rest of the industrial economy is only now catching up. And here is what they are not telling you. Once the strongest grades move beyond elite aerospace programs, the shock spreads into sectors that look unrelated on the surface. Science Direct. High-end carbon fiber was never just another product. It was a strategic bottleneck. China Daily reported that foreign firms, mainly in the United States and Japan, once controlled more than 90% of the global high-end carbon fiber market. That control shaped who could build the lightest aircraft parts, the toughest pressure tanks, the strongest drone frames, and the most advanced launch systems. China did not begin at the top. It had to climb through earlier grades like T300, then T700, then T800, and then the frontier grades. China Daily described the transition from lab work to factory stability as years of trial, with engineers checking equipment again and again under harsh conditions to stop tiny process deviations from ruining output. Imagine trying to bake hair-thin glass noodles in a furnace where a tiny temperature wobble destroys the whole batch. That is how unforgiving this industry is. China daily. And then geopolitics stepped in. SAMP reported that the United States and Japan tightened export controls on specialized equipment and technology for making high-strength carbon fiber. On paper, that looks like a way to preserve a lead. In practice, it also forced China to build deeper domestic capability across the supply chain. An analyst quoted by CMP said external pressure pushed China's industry toward technological self-reliance and control of the full chain. That is how a material story becomes a power story. If another country controls the thread inside your rockets, drones, hydrogen tanks, and high-end robots, then it quietly controls the ceiling on your industrial future. While you are watching this, China has already moved from a difficult start in T1200 to claims of mass-produced T1200. The gap grows every single day. But here is the part nobody is talking about. If China is first to industrialize the strongest grade, the biggest disruption may not begin in war. It may begin in the everyday industries already around you. SCEMP. That is the turning point. For a century, iron and steel looked permanent because they solved the mass production problem better than anything else. They were cheap, scalable, and good enough for most uses. But carbon fiber does not need to replace steel everywhere to change the world. It only needs to replace steel where performance compounds. Aerospace, launch systems, wind blades, pressure tanks, fast transport, robotics. Once those sectors move, the rest of industry starts redesigning around them. And the next question gets much bigger. If China can make the thread, where exactly does that strength go next? Because the answer reaches far beyond one factory line. The breakthrough becomes real the moment you stop looking at the filament and start looking at the systems it enters. China's T1200 carbon fiber is not important because it exists. It is important because China says it has entered industrial production with capacity in the hundreds of tons. That is what separates a scientific achievement from industrial leverage. High strength without scale stays trapped in a paper. Scale without high strength becomes commodity output. Put both together, and the balance of manufacturing begins to move. Think of a racing bicycle that suddenly becomes cheap enough for every delivery rider in a city. The bike is still a bike, but logistics, cost, and speed across the whole city start to change. CGTN SEMP. Start with aerospace, because aerospace tells the truth first. Aircraft and launch vehicles punish unnecessary mass with brutal honesty. Every kilogram added must be lifted, stabilized, fueled, and paid for. CGTN reported that a Chinese commercial rocket called Weiguang-1 uses a body structure about 90% carbon fiber composites, cutting weight by 25 to 30% compared with metal designs. That is not a cosmetic gain. It is like packing for a long trip and discovering that a quarter of your suitcase has vanished while you kept the same essentials. You move farther with the same effort. You pay less for the same mission. Most people will never hear this part. The big win is not a lighter shell. The big win is the chain reaction a lighter shell creates across fuel, payload, range, and cost. CGTN. Now shift to pressure vessels. This sounds obscure, but it sits under some of the most important systems of the next decade. Toray says its carbon fibers already go into compressed natural gas and high-pressure hydrogen tanks. Those tanks need walls strong enough to contain enormous internal pressure while staying light enough to move efficiently. Carrying gas in a heavy steel container works. Carrying it in a lighter composite vessel changes transport economics. It is the difference between hauling water in a metal bucket and carrying it in a hiking pack that spreads the load and lets you run. Here is what they are not telling you. When a country controls more of the best fiber, it gains leverage over the storage hardware behind cleaner vehicles, industrial gas transport, and parts of the future energy system. Toray. Then comes the industry most viewers do not expect. Wind power. People hear carbon fiber and imagine fighter jets. But the U.S. Department of Energy says carbon fiber spar caps can cut wind turbine blade mass by 25% compared with fiberglass, helping enable longer, slimmer blades and lower energy cost. Zoltec adds that carbon fiber is used primarily in the spar of blades, longer than 45 meters, with at least 20% weight savings when moving from an all-glass blade to one with a carbon fiber reinforced spar cap. Picture trying to hold a ruler straight. Easy. Now picture holding a telephone pole straight. Suddenly, the material decides whether the design is even possible. Longer blades sweep more air. More swept area means more electricity. So a stronger thread in one supply chain can eventually affect the price of power in your home. DOE Zoltec. And that is only one part of the energy story. The same 2022 review found carbon fiber demand in wind blades was projected to grow at more than 20% annually from 2020 to 2025, while pressure vessels were growing rapidly with lightweight fuel storage. Composites World notes that carbon fiber also appears in wind blade spar caps and other energy infrastructure. This is the detail that changes everything. The same material family that serves spacecraft also starts serving turbines, tanks, grids, and industrial storage. Once a material crosses from elite defense and aerospace into power infrastructure, it stops being a niche, it becomes a platform. Steel did that in the old age. Silicon did that in the digital age. Advanced composites may be doing it now. Science Direct Composites World. Now cut sideways again. Robots. ChemNet listed humanoid robots among the application targets for China's SYT-80 T1200 fiber. At first, that sounds like promotional overreach. But think about what a mobile robot actually needs. It needs limbs that resist bending, frames that survive repeated stress, and structures light enough to move efficiently without wasting battery power. A robot built like a steel cabinet may survive impact. A robot built like an animal skeleton can actually work. The analogy is simple. A sledgehammer is powerful because it is heavy. A human hand is powerful because it is precise and efficient. Robotics rewards the hand more than the hammer. Once advanced carbon fiber becomes more available, designers stop treating it like rare jewelry and start treating it like normal hardware. That is when prototypes start turning into products. ChemNet. There is more evidence that China is not making one miracle grade in isolation. CMP reported that CNBM launched 3 production lines in Jiangsu, including one facility capable of producing 1,000 tons of T1200 grade carbon fiber a year. China Daily separately reported that a first-phase T1000 production line in Datong achieved about 200 tons of annual capacity after continuous operation verification. Put those together, and a pattern appears. China is building a staircase, not a showpiece. T1000, T1100, T1200. Different grades for different markets. Not every machine needs the strongest fiber, but a country that can serve the full ladder can control far more applications. Not every road needs a race car, but a country that can build trucks, sports cars, and engines for both sets the pace for transport. CMP China Daily. This is why export controls cut both ways. They can slow a rival for a while. They can also force that rival to industrialize faster at home. Scamp quoted analysts who said foreign restrictions pushed China's carbon fiber sector toward full-chain self-reliance. Nobody noticed this until it was too late. The attempt to block the material may have strengthened the incentive to master it. And once a country learns to produce the chemistry, the equipment, the precursor, and the stable factory output domestically, the leverage starts to flip. While you are watching this, China has already moved from catching up in carbon fiber to setting the pace in some high-end grades. The gap grows every single day. But here is the part nobody is talking about. The real turning point is not one stronger thread. It is one stronger thread linking aerospace, energy, transport, storage, and robotics into the same strategic map. And once you see that map, the story stops being national. It becomes personal. Look at your own life, and the shift gets uncomfortably close. China Daily described carbon fiber as material for rocket shells, aircraft fuselages, wind turbine blades, hydrogen storage tanks, high-speed train noses, marathon shoe plates, fishing rods, and bicycles light enough to carry with one hand. That spread tells you something important. When one material starts showing up in transport, energy, sports gear, and industrial hardware at the same time, it stops being a specialty and starts becoming a platform. Plastic once did that. Steel did that. Silicon did that. Advanced carbon fiber may now be crossing that line. The U is probably already inside. They just do not know it yet. In this case, it is the lightweight design logic that already shapes the planes you fly in, the goods that move through logistics networks, and the energy systems feeding your home. China daily. The global implication is simple and brutal. Carbon fiber does not need to replace iron in apartment beams or ship anchors to make iron obsolete in the places that matter most first. It only needs to displace metal where performance multiplies. In aircraft, every kilogram saved can mean more range or less fuel. In drones, it can mean more battery life or payload. In wind blades, it can mean bigger swept area and more energy capture. In pressure tanks, it can mean lighter storage and easier transport. In robots, it can mean lower power draw and faster movement. It works like taking ankle weights off an athlete before the race starts. The athlete does not change, the result does. That is why countries that dominate lightweight advanced materials gain more than export revenue. They gain speed, science-direct DOE. That speed creates winners and losers. Nations with strong carbon fiber ecosystems can lower dependence on imported high-performance materials and move faster in aerospace, drone manufacturing, launch services, robotics, high-end vehicles, and energy hardware. Nations without that stack face a hidden tax. They wait longer, pay more, or accept performance ceilings set somewhere else. CATSE, AMP's reporting on export controls and domestic Chinese production lines outlines that split clearly. One side tries to preserve technical lead. The other side builds around the blockade. Once that cycle matures, supply chains stop feeling global and start feeling strategic. The cost of flights, packages, vehicles, and power can eventually reflect that shift long after the chemistry story leaves the headlines. Sam P. But this is not a clean victory story. Carbon fiber comes with problems. It remains hard to make well. It can stay expensive. And the waste challenge is real. Composites World notes that while more than 80% of a wind turbine is typically metallic and recyclable, the increasingly long composite blades pose major end-of-life recycling problems. So the future here is a trade. You gain lighter machines, better efficiency, and stronger performance. You also inherit harder recycling, more complex disposal, and supply chains that demand tighter precision. Think of swapping a simple steel toolbox for a carbon racing bike. You gain speed, you lose simplicity. Most people will never hear this part because every breakthrough sounds clean at the beginning. Real industrial revolutions arrive with a cleanup bill attached, Composites World. There is also the question of diffusion. Once China proves it can manufacture T1000, T1100, and T1200 at stable industrial scale, the next fight moves from invention to spread. Which firms get priority supply? Which sectors lock in early? Which countries choose to subsidize domestic alternatives? Which buyers decide the risk of dependence has become too high? Here is what they are not telling you. The decisive battle usually starts after the breakthrough, not before it. The company or country that wins is often the one that gets the new material quietly embedded into thousands of ordinary products before everyone else finishes debating the announcement. And that is why this story matters to you even if you never touch a rocket or a robot. You live inside systems built on materials choices made far upstream. The next car you buy may carry more composite structure. The next drone delivering medical supplies may rely on lighter frames. The next wind farm feeding your grid may depend on carbon fiber spar caps. The next generation of warehouse or household machines may move more like animals than appliances, because lighter structures finally made that efficient. While you are watching this, China has already spent decades climbing from T300 to the high end of the market. and the gap grows every single day. Nobody noticed this until it was too late, because a filament never looks as dramatic as a chip fab or a warship. But the filament slips into both, and this is where the emotional stake lands. Strength is not an abstract contest between labs. It decides what your country can build, what your employer can sell, and what your family pays for movement, power, and protection. If one nation gets lighter aircraft, cheaper launch services, stronger drones, and better energy hardware first, the rest of the world does not stand still and wait politely. It buys from the leader, copies the leader, or falls behind the leader. That is how materials power works. It spreads like better running shoes in a marathon. One runner upgrades first. Then the whole field feels slow. While you are watching this, China has already turned years of materials research into factory lines, product pipelines, and strategic leverage. The gap does not announce itself with fireworks. It shows up as lower costs, faster machines, and industries that seem to accelerate for reasons most consumers never see. That is why this story is bigger than carbon fiber. It is about who gets to define the new normal before everyone else notices it first, quietly. Scamp China daily. So here is the final reframe. The biggest threat to iron was never rust. It was losing the jobs where modern power is decided first. A thread thinner than hair now reaches strength above 8 gigapascals, enters production measured in hundreds of tons, and moves into rockets, wind systems, tanks, drones, and robots that shape the next industrial map. So here is the question worth sitting with. If the future belongs less to the heaviest material and more to the smartest one, what happens to countries, companies, and workers built around the old definition of strength? Drop your honest answer in the comments. And if this video showed you something the usual headlines consistently skip, hit like and subscribe, because the next shift is already happening, and we will cover it the moment it arrives.